Alright, so this is week number 8 in the Digital Fundamentals course. Today we are talking about flip-flops. So flip-flops are very useful circuits that we start to use, and they are useful because they are a memory or latching type of circuit. So everything we've done so far, the outputs change and stay as they are depending on what the inputs are doing. This is our first circuit we're going to do, where the inputs, we can turn on an input and our outputs will change, and then those outputs may stay in that state regardless of what the inputs do after that. So this has a lot of uses for us when we start doing counting or bit shifting or things like that. So this is when we can actually start to remember what things were in the past, basically. So this creates some ability to have memory for us. So the first one we're going to talk about is the set and reset, or the SR. So that is a set reset type of flip-flop. So, sorry, we're going to call that an RS. Flip-flop, and that stands for reset and set. So you'll notice the wiring of this. We are now starting to do what we call feedback. So we get some feedback going. So you can see here where we have wires from an output that actually go back into an input of another gate, and then likewise we have the output of that gate goes back as an input to the gate that it came from. So we have some basically little loops forming in these circuits now. So let's see how that affects how this actually operates. So like we said, the RS flip-flop is the most basic type of flip-flop. To understand how it works, let's write out the truth table for this. So when we talk about this, we're going to have a set input, a reset input. I'm going to call this one R. We're going to call this one S. And we have two different outputs we're going to use. One is called Q, which is our main output. And then we have another one that we call Q bar. And as we know, Q and Q bar are always going to be opposite of each other, or at least they should always be opposite each other. So let's look at this chronologically, basically in time. If we were to create this circuit, and we will make this in our very first part of our lab, and if we start it up, so we build this circuit, we turn on power, and what do we get? So when we very first start out, remember this is set, this is reset. When we first start out, we have a 0 here and a 0 here because we haven't turned any of our switches yet. So if we have S is a 0 and R is a 0, everything else in the initial state will be a 0. So if we look here for a NAND, if we have any kind of a NAND, because these are NAND gates, if we have anything with a 0 in it, the output of that is going to be a 1. So here we have a 1. That comes up here, creates a 1 up here. This is going to create a 1. That comes down here, gives us the 1 down here. But basically the result of this is we are going to get a 1 and a 1 over here on our initial power-up state. So that is how we get this. Okay? That is when we first power this on before we turn any switches. You should get this. Now, important thing to remember when we are using, we're going to call this the prohibited state here. We should never actually get this because we always want to have either the S or the R inputs. Should always be, one of these should always be a 1. We want to do that. So one thing that's weird about the RS flip-flop is that we are going to say that we are going to turn this to 0 to activate. So it's actually like an active low input. So having them both as zeros, this is a state that we will not have. So we don't want to get this state. Okay? Because basically right now we have a 0 and we get both Q and Q bar on at the same time. That's not good. Okay? So let's say we actually want to do a set function. So to do the set function, like we said, turning to 0 is an activate. So turning S to 0 and holding the reset at 1 will be a set function. So when we do that, we'll see here, we put in a 1 right here. And we know that putting in a 1 when we already had a 1, putting in a 0 here, anytime we put in a 0, that's going to cause a 1 over here. That 1 now comes over here. This one is going to be a 1 as well. A 1 and a 0 here. A 1 and a 1 there, sorry. That's this condition here. That causes us a 0 here. That 0 comes back up here. So this is how we get our Q and our Q bar here. So this ends up in this state here with the 1 and the 0. Okay? So kind of follow that through, how that gets to us. That will create a set condition. Set meaning that we have the Q output is on, the Q bar output is off. We are now in our latched or our set condition. Here's the weird stuff. If we now deactivate the set, which means we're going to turn them both back to a 1 and a 1, what you'll see is our outputs are just going to hold where they were before. So now when we put in a 1 and a 1, this will depend on what the last state was that we're already in. But if you follow this through, if we go from the set position to this position, it's just going to stay as it was before. So it'll actually stay as 1, 0. Okay? Now if we want to do a reset, we're going to put in a 1 and a 0 on the R. If you follow this through, you'll see that you get a 1 down here and a 0 here. So that is our reset because our Q is now off, our Q bar is on. Now from this position, if we return to this state here, now the same state here is now Q is off, Q bar is on. Okay? So notice this input combination here of 1 and 1 is the exact same combination that we had back here, except this combination gives us Q and Q bar is up, Q is on, Q bar is off. This one gives us Q is off, Q bar is on. The difference between these inputs are the same in both conditions, but the difference is we went from the set condition, this is where we were, and we moved to the hold condition, versus we were in the reset condition and moved to the hold condition. Different combinations of input, same combination of inputs gives different results because it's a matter of where were we last, okay? So this is the whole remembering where you were before you go back to normal, okay? So that is how this actually works as a latching circuit. So now we'll jump over to TinkerCad and show you what that looks like there. Show you this running in TinkerCad. Okay, we are going to look here at the TinkerCad version of the SR flip-flop. So this is the SR, or set reset flip-flop. So I have the circuit built here on the screen. So we can see this running. So I'm going to put this in simulation mode. I'll start the simulation. So what we've got here, two LEDs, one representing, the red one representing Q, the green one representing Q bar. And as you can see, I've got two dip switches I'm actually using here. First one is going to represent S, or set. Second one is going to represent R, or reset. And I've got my 00 chip, which is the NAND chip. I've got it wired up like in lab 4, like in the lab part A. And the down position here represents a 1. So we can see here, this is 1 and 1 right now, which represents both set and reset in the, basically the off position. So remember with the SR, to activate either the set or the reset, you turn them to the 0 state to activate them. So if these are both in the 0 state, you'll see both LEDs are on. In the SR state, so I'll just show you this here. So if we do a set, so turning that one to the 0 state and then back to the 1, you'll see that gives me the Q is now on. So I have the Q is on, so this is in the set position. And you see how I can turn this on and off all day long. That doesn't change at all. It does change if I click the R, or reset. By doing that, that turns the Q off and the Q bar turns on. Okay? So you can see how this is basically a memory circuit. So if I want to set the memory, I need to turn the S from 0 back to 1. That gives me Q. If I want to reset it, I toggle the other one. It doesn't matter how many times I toggle it, it stays the same. So I can set and I can reset. Okay, set and reset. Okay, and that is the basic principle of a flip-flop, is being able to take that signal and lock it in place, and then it doesn't matter after you lock it in place what you do with the signal after that. It doesn't need to stay. Your input signal doesn't need to stay on. It is latched in, and you're basically creating a latching circuit by doing this. Alright, and that has lots of uses for us when we're trying to create memory circuits. Alright, so that is the SR flip-flop demonstrated. Okay, so now that we've seen that in TinkerCad, here, let's move on to the next circuit we're going to talk about. So this is the clocked version of the RS flip-flop. So you'll notice here, this is part B of the lab. This portion is exactly the same as what we just did. So what we're adding now is this stuff over here. to the left of that. Let me grab another different color. So we're adding this portion here. And we call this a clock. Now what the clock does, this prevents any changes from happening until we actually fire this clock pulse from off to on. Okay, so it's on this transition of the clock pulse. Call this clock. That we actually get a transition of Q and Q bar. So we can change the set and reset as much as we want, but it's only what position these are at the time when this clock pulse happens that actually matters. Okay, so we'll demonstrate this in TinkerCad as well. So the main part of the flip-flop circuit will be in the hold state unless the clock input transitions to on. This is a rising edge transition. So rising edge transition meaning it is when this here happens that we actually get the transition and the switch of these signals. So what you'll see, the other thing we're going to see now as well, is that now this becomes an active high circuit. So if you actually want to set if you actually turn S to 1 and R to 0, which is the opposite of the this works the opposite of the RS. And to reset it, it's R is equal to 1 and S is equal to 0. Okay? And then what we need is a positive transition of the clock pulse. So we should never get this condition here. We should not get. That is set and reset on at the same time. We should not get that. But if we want to set, what we should get is turn on the set input. That should give us Q. If we turn on only the reset input and clock it, that should give us the Q bar only. And if we turn on neither of them and clock it, we should get no change. It should stay in the state that it was. And we will demonstrate this in TinkerCad as well. And this is part B of the lab, which we will demonstrate in TinkerCad. Okay, this one is the clocked SR flip-flop. So the difference here, we have our S, our set, our R signal. We now have this clock signal. And we have it wired up as it's called for in the lab. We have our Q and Q bar. So the difference with this is now nothing changes when we flip our S and R switches. Before, to set or reset, we would turn these to a 0. We now turn them to a 1, so that operates differently there. And now what we do is we actually turn this clock signal from 0 to 1 back to 0, so just give it a pulse, a 1 pulse, in order to actually enact any changes. So if we clock that, you'll see we get a change. So that is a 1 and a 1. That gives us both lights. If we want to do a reset, we would give it just the R only, and then hit that clock, 0 to 1 back to 0. And you can see I can change the S and the R as much as I want, nothing happens. If I want to do a set, I give it set, the S as a 1, the R as a 0, and now if I clock it, you'll see that gives me the Q and not the Q bar. Just a second for that lights to change. If I want to flip it back, I'll change those two switches there. I now have the R and not the S, and I will clock it. And I get that signal now, which is Q bar and not Q. Alright, so that is the clocked version of the SR flip-flop. And that's the way we're going to see a lot of our flip-flops work, is with a clock signal, so that we can manipulate the sets and resets. And it's only when we receive that clock pulse that anything actually changes. Okay? That is the SR clocked flip-flop. Alright, so now on to the D-type flip-flop. D standing for data. This is one of the simpler ones, and this one we are not building in out of individual gates because we actually have a chip that does the D-type flip-flop for us all contained in one chip. So it's actually simple because we have a single clock input and we have a single data input. Okay? So what you can think of is having this work as a RS flip-flop, as a clocked RS flip-flop. But if you took an inverter and took one input and called it data and had it go directly into the S and invert that signal and put it into the R, that would work essentially the same way. Okay? So 1 equals S and 0 equals R. This goes to set. And then this combination goes to reset. And basically what we're saying here now is that data equals 1 means that's going to be a set. Data equals 0 is going to be reset. So it's basically doing the same function as the clocked RS flip-flop, but only with one incoming data line instead of having to use two switches for R and S instead, because R and S should always work opposite to each other. The one thing you can't do is the hold signal with this. Okay, so that is the D-type flip-flop. And that really simplifies the data table as well, because basically if D is off, you get Q bar when you clock it. If D is on when you clock it, you get Q. Okay? So when we do this in the TinkerCad, I forget which chip we have, if it's an exact 7474 chip or not, but we do have a D-type flip-flop chip in TinkerCad. So you'll see here, we have our data, we have our clock, we have ground, we have power, we have two different flip-flops here, so we'll only look at this half of it, other than the power. And then we've got a couple other things here. So we've got Q and Q bar. And then we've got two other signals that we need to talk about. We have what we call an asynchronous preset and an asynchronous clear. You'll see these have bars over them as well, so that means to activate them, you turn them to 0. So if you turn So if you turn this signal to a 0, regardless of what anything else is doing, so regardless of the clock, regardless of the D signal, this will, if this goes to a 0, you are going to set it. You will set the Q and Q bar. You'll set Q to, we're talking about 1, we're talking about Q. You'll set Q to a 1. If you turn the clear signal to a 0, you will reset the flip-flop to 0. Okay? And that operates independent of the data and clock signal. So if you look at this here, we call this asynchronous set and asynchronous reset. So we're saying it doesn't matter what these signals are doing. If you make this a 0, you're going to get Q. If you make this a 0, you're going to get Q bar. If you turn them both to 0, you're going to get this prohibited condition where they're both on. You don't want that. Okay? And then just working normally. We just want to hold these both high all the time just to run normally. And then if D is on at the time when we clock it, we'll get Q. If D is off at the time when we clock it, we'll get Q bar. Okay, and we can demonstrate that in the lab. This is what our circuit looks like. So we need all these signals. We'll need the preset. We'll need the reset for clear. We'll need the data signal, and we'll need the clock signal. And these all wire in like this. Okay? That is the D-type flip-flop. And we will, in part C, we can verify our truth table. Alright, this one is the D-type flip-flop. And what we've got here, you'll see that we have just our single flip-flop chip here. We have, again, our Q and Q bar. And then we've got 4 different inputs we're going to use. We have our data line, our clock, our preset, and our clear. So those are 4 different inputs that go into the flip-flop. 2 outputs being our Q and Q bar. So let's look at how this works. So first of all, let's look at the preset and clear. Regardless of what data and clock are doing, we can always set it to either the Q or Q bar with a preset and clear. So normal state for these will be 1s. If we turn either 1 to a 0, its action will take effect. So if we want to give it a preset, which means load it as a 1 or load it as Q, we turn the preset to a 0. So if we do that, toggle that to a 0, and then back to a 1, that gives us Q. Same thing with the clear. If we toggle the clear to a 0, then back to a 1, that switches us to Q bar. If we put them both as a 0, that gives us an undefined state, and they both are on. We should not have that. Okay? So now that we have Q bar showing there, what we do is we set our data how we want to store this. So if data is off and we clock it, we get Q bar. If data is on and we clock it, we get Q. So every time I clock it now with data on, we'll continue to stay with Q. If we turn data off and clock, we will go to Q bar, and every time I clock it, we are just relatching or resetting the flip-flop as a Q bar. Turn that back to on at data, and clock again. You see how now we have Q. Okay, so basically we have D for data. Whatever the state of that is at the time when we clock it, that is what our output is going to be. We can preload our output independently of the data and clock with this preset and clear as well. That is how the D-type flip-flop works. And then the final flip-flop we're going to do is the JK type flip-flop. And this is kind of considered the universal flip-flop because, like when we talk about universal, like with the NAND gate, universal meaning you can create any other type of flip-flop you want by using this type of flip-flop. Okay? I'm not exactly sure why it's called JK. This essentially works like an SR flip-flop with one major exception to it. So the J is basically considered the set, the K is considered the reset. If you turn both of these on at the same time, if they're both off, that is a hold signal. If you turn them both on, is the unique thing about this one. Turning both of these on at the same time and clocking it will give you a toggle. That means that it will change from whatever state it was in to the opposite state. Now this becomes very useful when we start doing things like counting and doing bit shifting and things like that. This becomes very useful because you can string a bunch of these together and create a counter because you can toggle bits back and forth just by clocking them. Okay, so we have the 112 chip here we're going to talk about. I know in our TinkerCad, I think it's the preset that we do not have. So we have a comparable chip in TinkerCad that we will show in a minute here, but it doesn't have the preset, I don't think. But it does have two JK flip-flops on it. We've got J, we've got K, we've got ground, we've got power, we have clear or reset, we've got Q, we've got Q bar, and we've got our clock input. Okay, so we can do all these things. Yeah, like I said here, we have the C73 chip in TinkerCad, so we'll do that. So you can see we have, and it does wire a little bit differently. Our power is on pin 4, our ground is on pin 11, and then we are going to use K, J, Q and Q bar, and then we have clock pulse and reset. Okay, so we will wire ours like this. So like we said there, we have reset but not preset, so we can't verify this in TinkerCad, but we can do all the other ones. So turning reset to a 0 gives us Q bar, regardless of what clock J and K are doing. We never get the prohibited condition either. And then leaving that on, now we're operating as a JK flip-flop. And we should be able to see the hold. If we have J and K both off and we clock it, it'll stay in the same state. K on when we clock it will give us a reset. J only on when we clock it will give us a Q. And then this toggle one, which is the most interesting one, if you have J and K both on and just leave them on, every time you clock it, this should change to the opposite state. Okay, so it just should flip back and forth. Alright, so we can demonstrate that one. And you'll see that our truth table, this is actually the truth table for the, we call this the 83 chip. 73. This is actually the HC73 tooth table right here. So this is the 112. This is the HC73 that we actually have in TinkerCad. So this is the TinkerCad version of the truth table. So when you actually test this out, this is what you will see. So you'll wire it up like this. We don't have the preset, so don't worry about that one. But everything else you can wire. And you should be able to test out this table. Okay, so we'll test that in TinkerCad. Okay, this one is the JK flip-flop. This is our final flip-flop we're going to be dealing with. This one is interesting because it does a couple new functions. For one in particular, the toggle function that the other ones don't do. So for this one, according to the book, now we can't do the one that's in the book or in the lab. We don't have that chip. I think it's a 112 chip that it shows being used. We have a 73 chip, which is a JK flip-flop, but does not have a preset function to it. So ours works a little bit differently. So we can't do the asynchronous preset. We can do an asynchronous clear. Okay, so I'll demonstrate that. So it has two inputs that it calls J and K. J is basically the set, K is basically the reset. I'm not sure why they call them J and K, just to confuse people, I guess. It also works on a clock, so this is another clocked flip-flop. And I'll show you some interesting things here. So first off, this one operates, the 73 operates a little bit different in that so right now you can see I have the Q. If I set the clear to a 0 and then back to 1, anytime I set the clear to a 0, I'm going to get the asynchronous clear, so that gives me Q bar instead of Q. No matter what I do, if that clear is set to 0, nothing I do is going to affect the operation of this. Okay, so I can't change that as long as that clear is set at 0. Once I set clear to 1, now I'm able to get some different operation out of this. So if I have J set to 1 and K set to 0, and I do a clock pulse, now for this one, it is actually a negative clock pulse that will trigger it. So setting my clock from 1 to 0 and then back to 1 is what actually triggers it. So you can see that sets my output now as Q. If I change these around, I now have J as 0, K as 1, and I clock it again. That does my reset function. Now the interesting thing about this one is if I set both my J and K as 1, every time I clock it at this point, it's going to do a toggle function. So it'll just change the output. So if it was off, it'll change it to on. If it was on, it'll change it to off. So every time I toggle this now, you see now it's on. That's going to on. Now it's going to off. Now it's going to on. So this is basically just flipping back and forth every time that I toggle. And this becomes very useful with some things that we start to do later on when we start doing counters and bit shifting. This becomes very useful for us. Okay? And once again, I get back to here. I'll set it. And I can do a asynchronous clear just by doing that. Okay, so that is the JK flip-flop. A 112 is what we show in our paper lab and in the PowerPoints. This is with the 73 chip, which we have in TinkerCad, so we can do basically the same things, except we can't show the asynchronous preset. Okay? But this works pretty much the same way. So that is the JK flip-flop. And then the final thing that we'll talk about in lecture today, we actually won't do this one in TinkerCad, but this is basically adding a Debounce circuit to the JK flip-flop circuit. So we have our JK flip-flop, which we did already. Don't do that. But what you may notice, and you really don't see this in in TinkerCAD because everything switches very cleanly. But if you were making these out of real dip switches, when you turn your dip switches, we're assuming that when you turn this, you go from off to on, to off, to on, to off, to on. Well, what happens if when you turn this switch with your screwdriver or whatever it is, what happens if you go to turn the switch and you get kind of partway between where you're turning it and you actually get a signal that looks kind of like that, where it kind of bounces back and forth, where you're just kind of making contact but then not? You might get something that looks like this. Okay, so the problem is if you're in toggle mode, this is supposed to be, you're supposed to be switching that once. But depending on the timing of this could be interpreted as 10 switches, just because it's kind of a chattery signal that's bouncing around as it makes contact. The problem is if you're toggling, you might switch on to off to on to off to on to off every time this happens. Okay? We don't want that to happen. So what we need to do is add something called Debounce. So we would call this a bouncing signal here. So we want to debounce this signal. So this is basically our RS flip-flop signal. That's our RS flip-flop wiring. If we put that out here, what we did prove in the very first lab, this creates a completely square output because of the nature of the way that it creates an output from this. So what we can do here is when we have this as our clock signal, this will read as when you transition, it will take a chattery signal like this. It takes chattery signal and turns it into a nice clean signal that looks like this, which gives nice accurate counts. Okay, so that is the purpose of a debounce circuitry, which is what we are adding in right here. Okay, so that is the debounce. And what you will see, if we actually did this in the lab, we're not going to do it in the lab because it doesn't prove anything for us, because TinkerCAD doesn't have a debounce problem. If you do this on your breadboard, you may experience a debounce problem though. You will see when you actually toggle this with the debounce circuit in, it performs much more like you think it should if you do this. Okay, so that is adding a debounce circuit. And that is it for flip-flops. Okay, so do we have any questions about flip-flops? If you do, you'll have to wait until Thursday. Anyway, we will see you. Good luck with the TinkerCAD portions. Remember to give all those a try and submit your final one. And we will see you on Thursday. Thanks.